Let's now move on to the last question. The third round always has 6 questions. Question says, let n be the set of positive integers. In other words, the counting numbers 1, 2, 3, 4. And let f be the function whose domain is, the inputs are natural numbers, n, and the outputs are the natural numbers including 0. All right, those are called the whole numbers. This is the symbol for that. And let this function here have the property that f of mn is equal to mfn plus n times f of m. Okay, we have to just understand this. This function, what it does is that it takes the image of m, f of m times n, there it is, and then adds it to the image of n and multiplies by m. That's it there. Okay, so this is the rule. And let this rule be true for all positive integers, m and n. It's also given that the value of 2024 by the function f is 10,120. Now prove that there are 2 positive integers m and n with m different from n such that f of m equals f of n. In other words, you've got 2 separate numbers whose outputs are the same, m and n, f of m. They both go to the same thing. All right. And these must be different. Okay, now this is quite a challenging problem. So just try to concentrate. All right, let me just write down the rule because that is what we're going to use over and over again. The rule is f of mn equals f of m times n plus m f of n. That's given. And this is for all natural numbers because the inputs are all counting numbers. All right, now I just want to say, analyze this thing here. The conclusions we can make from this. You have this f of, if you multiply 3 things, we got the f of a product here, but f of 3 things, it's the same as f of the product of 2 numbers. If we say this is f of AB times C, and then plus. Well, let's look at it this way. This ABC can be regarded as A times BC. So let me do it like that. So this is f of A times BC plus A times f of BC. I'm regarding this as a product of that and that. Now, this one here we already have a rule for, because this is FA times BC, and this is f of this A times, and f of BC is FB times C plus B times FC. Right? This is the rule that was given to us. F of Mn is M times F of N plus N times F of M. So, and if you expand this, you get this. So you have F of ABC. It's like this. You write down, because there are three terms here, you put ABC, right? And then you take F of the first one, you take F of the second one, and take F of the third one. That's what we got here. A times F of B and AB times F of C. So there's a simple way of calculating the product. So this is your first conclusion. Right? Sorry, let me just write this thing neatly. Sorry about this. I just wanted to illustrate the way you remember the formula. So this is F of A times BC plus A times F of B C plus AB F of C. Just remember that this is the value of the image of a product of three numbers. Now, the second useful thing is that F of A to the power of N is equal to N times A to the N minus 1. If you have done calculus, this looks very much like the derivative of a power, N times A to the N minus 1, but you have to multiply this by F of A. All right, and this is true no matter what positive integers you take. You can take for A and N. All right. Now, if you want to prove this, a simple way of proving it is as follows. See, this rule here can be applied not only to three numbers, it can be applied to any product. All you have to do is to take the F and apply it to each of the terms in that and add everything else. All right, so let me see whether I can prove the statement here. So we have F A to the N. Now what is this? This is F of A times A times A all the way up to A, and the N of these. Right. So if you remember what I just did here, I can say that you apply F of A to the first one, this one here, and then multiplied by all the others. Now this is A to the N minus 1, the product of the remaining ones, plus now you got F of A. Now you apply A to the second one, so leave the first one as it is, and now you have F of A here, and then you multiply it by the others, right? And you take the others together with A, all you are doing is you're missing out one of the terms, yeah? So again, you have A to the N minus 1. This will be A to the N minus 2, because I take this A, take this, and the N minus 2 left. If you keep going on like this, You come to the last one. The last one is all the first few n minus 1s here. And you apply f to only the last one. Right. Now, if you look at this carefully, you'll see that here I've got a times a to the n minus 2 is a to the n minus 1 times f of a. So I've got a to the n minus 1 times f of a. Here I've got a to the n minus 1 times f of a. And here I also have a to the n minus 1 f of a. And the n of these, right? So therefore, this is n times a to the n minus 1. And this is exactly what we've got here. For example, f of a cubed is 3a squared f of a. Right? If you let n equal to 3. Okay, so just try to remember this, because I'm going to delete this entire page. There are two things here that we concluded from the formula itself. Okay, now what I'm going to do now is I'm going to have a look at a thing like this. This is the third conclusion. Okay, we can't come to this yet. Sorry. Okay, what I'm going to do now is I'm going to look at what is given. We are given that 10,120 is equal to f of 2024. That's the only piece of information that is given. Okay. So let's write 2024 as a product. You can factorize it. It is 8. 8 goes into this exactly, the last 3 digits. 8 goes into the last 3 digits. The 8 goes into this. That's 8 times 253. And 2 plus 3 is 5. So this is 11 goes into this. 23. So now you have a f of a product of 3 numbers. So as we saw before, this is f of 8 times 11 times 23. And then it's plus 8 times f of 11 times 23. And then the last one is plus 8 times 11 times f of 23. Okay. We proved this earlier. Okay, 11 and 23 are primes, but 8 is not. So f of 8 is actually f of 2 cubed. And we saw that this is 3 times 2 squared times f of 2. And that last formula we did. F of a to the n is n times a to the n minus 1 times f of a. So this is 2 squared is times 3 is 12. F of 2. So this is equal to 12 f of 2. Okay, I'll just replace that. Well, instead of rewriting this whole thing, I'll replace this f of 8 by 12 times f of 2. Oh, God. Sorry, that doesn't look very nice. let's make this thing 12 times f of 2 times 11. Right. Now, this thing here can be factorized. Actually, if you multiply this by 5, you'll get this. You see? So this really is 5 times this. So the left-hand side can be factorized. We factorize 2024, there it is, yeah. So that is 8 times 11 times 23. This is 8 times 5 times this, and this is these product of these three numbers. Okay, now I want you to observe something here. You see, this number here is, let's take 11. This number here is 11 times something. Let's call it 11x. This is also 11 times something. Now this is 8 times f of 11 times 23. But this is 11 times something. 11 times z. So what happens there is that you can make this your subject. You'll have 8 times 23 f of 11 equals 11 into x minus y minus z. See? Can make the subject. But the point about this is that 11 is a factor. We write factors like this. 11 times some integer is equal to this. Now 8 and 23, they don't have 11 as a factor. In fact, this number here and 11 have got no common factors. The HCF is 1. Or the other way of saying it is that these two are co-prime. So whenever you have a situation like this, it means that 11 is not a factor of this product. So 11 has to be a factor of this one here. See, 11 is a prime number. That's one of the reasons for this. Because when you factorize f of 11, whatever it is, the 11 will be contained in the factorization of this, not there. In other words, 11 is a factor of f of 11. All right. Now, I just chose 11. I could have chosen 23, which is also a prime number. And I could have come to the same conclusion. And then 2 is a prime number. So I could have come to the same conclusion. See, like how 11 is a factor of f of 11. Right. So what does all this mean? It means that we can write this thing as an equation. We can say f of 2 is 2 is a factor of it. So f of 2 is equal to say 2, say p, or 2, whatever, 2p plus f of 23, sorry, f of 23 is equal to 23 times q, because 23 is a factor of this, and f of 11 equals 11 times something else. Okay. Now I just want to digress a little bit here. You see, let's go back to our original formula. We had f of mn equals f of m times n plus m times f of n. And this is true for all natural numbers. So I can make m and n both equal to 1. I can substitute any numbers here, but I want to substitute both equal to 1 because I noticed that in that case you got f of 1 times 1, and here you got 1 times f of 1. M is 1, you see. So you got f of 1 equals f of 1 plus f of 1. That implies that f of 1 is equal to 0. Right. Okay, now that's quite useful. So f of 1 is equal to 0. Let me, I need this equation here, so I'll just rub off all the other things. Now just ignore this equation which I left here, because I'm going to go down to the last thing we said is f of 1 is 0. Right. Now we want to prove that you can find two numbers, x and y, both going to the same thing. Right. Now, if there exists, if there is an n greater than 1, I'm going to put the n here, n greater than 1, I don't want these two to be equal. So, and the inputs are all natural numbers. I want to avoid the first natural number, n greater than 1. If we have this situation, then we are done. So this was the goal. The goal was to find two different numbers whose outputs are the same. If you have n greater than 1, if there is an n greater than 1 such that f of n equals 0, then we are done. All right. So let us assume that this is not happening. So suppose then that for every n greater than 0, n greater than 1, right, that f of n is not 0. We know that the outputs are all greater or equal to 0 because we had n 0 on the right-hand side, remember? So f of n is greater or equal to 0. But we don't want f of n to be 0 now. We are assuming that if this is 0, then we are done. So we're going to assume that this is always greater than 0. All right, so this is going to be our starting point. I should have said this thing earlier on. So here you have, like for instance, so here P, none of P, Q, and R are now 0. Because if any one of these is 0, then you'll have a contradiction. Because we're saying for all positive n, f of n is greater than 0. So that means that f of 2 now is greater than 2. So it means that P must be greater or equal to 1, which means that, so f of 2 is a multiple of 2, so it must be greater or equal to 2. F of 23 Let me just do this thing neatly. Sorry about this. I'm preserving this thing here for so long. Could have rewritten it instead of going through all this inconvenience. So we are saying now that f of 2 is greater or equal to 2, f of 11 is greater or equal to 11, and f of 23 is greater or equal to 23. Because it's equal to 23 times q, and q is not 0, so it's at least 1. So you have this. Now, the beautiful thing about this is that, in fact, you actually have that f of 2 is exactly equal to 2. Is equal to 2. F of 11 is equal to 11. And f of 23 is equal to 23. Right. Now, why do we say that? Okay, we say that to prove this now, we can prove by contradiction. Suppose one of these is false. Okay, say f of 11 equals 11 is false. Any one of them is false. So I'm going to say, suppose f of 11 is not equal to 11. So it has to be greater than 11. For example, right? Now I'm going to use this thing which I've been preserving it for so long. So what do I have? I have that f of 11 is strictly greater than 11. F of 2 is greater or equal to 2. And f of 23 is greater or equal to 23. And I'm assuming that one of them is strictly greater. So I have on my left-hand side, I have 5 times 8 times 11 times 24. Now it's equal to this. So I'm going to make this thing greater or equal to, this is 12 times 2. F of 2 is greater or equal to 2, you see, times 11 times 23 plus, here, f of 11 is greater than 11, strictly greater. So instead of putting greater or equal to, I'm going to make this thing here 8 times 11 times 23. F11 is greater than 11. So what I'm going to do is the left-hand side is strictly greater. Right, because one of them is strictly greater. And then here, f of 23 is greater or equal to 23. So I've got, this is greater than, because one of them is greater and the other ones are greater or equal to. Okay, so this is what you've got here now. This is 23. Now, you'll notice that 8 times 11 times 23 is a common factor right throughout. Let me divide by 8 times 11 times 23 in both cases. Now I've got 5 is greater than 8 times 11 times 23. This is 24. So I'm dividing by 8. So this is 3. I'm dividing by 8 times 11 times 23. 3. And here, 8 times 11 times 23, I'm dividing by that. And here I'm dividing this by 8 times 11 times 23. So I got on the right-hand side, I got 5. Now you see, you got 5 is greater than 5. Of course, this is impossible. So this is a contradiction. What I'm actually doing here is proving by contradiction. I want to prove that f of 11 equals 11. This was my goal. And I assume that it is not. And then I came to something which is impossible, that namely 5 is greater than 5. So therefore, our assumption that f of 11 is greater than 11 is false. So it means that these two are equal. Now you can use exactly the same arguments to show equality in the other cases. Same argument, nothing special about 11. So you've got so these now are equal. Right, which is very nice. Now we know not only f of 2024, but we know 3 other values: f of 2, f of 11, f of 23, and all of them are equal to themselves. Okay. Now I want to use this fact to calculate any expression, any number which has got the factors 2, 11, and 23, prime factors. I'm going to just focus on that. What I mean is, so let x be equal to 2 to the power of a times 11 to the power of b times 23 to the power of c. So I take a number whose factors are only these, because I know f of 2, I know f of 11, f of 23, so I can now calculate f of x. Right? F of x is equal to f of 2 to the power of a times 11 to the b, 23 to the power of c. We've seen this. Again, it's f of a product of 3 numbers. I can put 2 to the a here. And now I could put f of 11 to the power of b here. And I've got 23 to the power of c. And then finally, I have 2 to the a times 11 to the power of b times f of 23 to the power of c. So I can apply f to the first, apply to the second, and to the third. But we know that f of a power, we calculated that. So this is a times 2 to the a minus 1 times f of 2, this part here, right? A to the n is n, a to the n minus 1. I'm using that thing that we proved. And this is 11 to the b, 23 to the power of c. Here I've got 2 to the power of a. And this is b times 11 to the power of b minus 1. And I have, times f of, sorry. Now, f of 2, I'm not going to put f of 2 there, I'm going to put 2 here. I know that f of 2 is equal to 2. So in place of this, I'm going to put 2 here. And I should have had an f of 11 here, but I'm going to put 11 there. And you have 23 to the power of c. And here you have got 2 to the a, 11 to the b, and 23 to the c minus 1, right? Times f of 23, which we know is 23, right? Because we've got those. Now you can group together. See, this is 2 to the a. Right? And these two together give you 11 to the power of b. And those two together give you 23 to the power of c. So if you look now, you'll see I've got 2 to the a, 11 to the power of b times 23 to the power of c is a common factor. Is a factor of this, right? The remaining factor being a. Now here too, you've got 2 to the a, 11 to the b, 23 to the power of c. And these two together give you that. So again, you got the same factor. You can take it out. And in this case, also, you got the same factor. The thing that comes out is a c. Well, I had a c here. The f of 23 to the power of c is c times 23 to the c minus 1. So now remember, this is your x. There it is. So this is your x. So this is actually equal to a plus b plus c times x. And I've got f of x on this side. All right. So all this calculation allows us to conclude the following, that let x be equal to this, then I'm going to put this right at the top now. In fact, I'm going to take everything out here. Hopefully I can remember all these things which I wrote. So what we've got here is, if x is equal to 2 to the a times 11 to the power of b times 23 to the power of c, then f of x equals a plus b plus c times x. All right, a very nice formula. So now we can calculate f of x for any x, as long as you know its factorization. See? Into products of primes involving 2, 11, and 23. So you've got the f value for a lot of things. So now we might be able to find, so let's try to find x not equal to y, but f of x equals f of y, right? Now the x is going to look like this. So let x be equal to 2 to the a times 11 to the power of b times 23 to the power of c. And y, I want y to also look like that. But now it's a different factorization. Let's call it 2 to the power of p times 11 to the power of q times 23 to the power of r. Right? We want to let x not be equal to y. But we want that f of x is equal to f of y. And f of x we just saw is a plus b plus c times x. I'm going to put this down here. A plus b plus c times x. This is the f of x equal to p plus q plus r times y. Because I'm saying that f of y, as long as your y has got these prime factors, then f of y is equal to the sum of the exponents, p plus q plus r times y. Okay, so I have this situation, and I want to find out whether I can find these numbers. Can we find a, b, c, p, q, r that makes this true? And of course, if you know these three numbers, then x is also known, because x is in terms of a, b, and c, and so is y. All right, now this is a tricky part. We don't know whether we can find these, but as a starting point, just to simplify things, suppose we want to look for a solution where you have this equation with x being equal to that. See? So let us assume that, not assume, we will try to see, just to simplify it, whether A equals B gives us a solution. This will become apparent just now. So let's make both of these A. So what do we have? Then we have that 2A plus C times x. This x is 2 to the power of A times 11 to the power of B times 23 to the power of C. Now, A is equal to B. So I can make 11 to the A here, right? And this is now equal to P plus Q plus R times Y. Y is 2 to the power of P times 11 to the power of Q times 23 to the power of R. Okay, now I've got 2 to the A times 11 to the A is actually 22 to the power of A. So on the left-hand side, I've got 2A plus C. I've got 22 to the power of A times 23 to the power of C equals P plus Q plus R. And I've got 2 to the power of P, 11 to the power of Q, and 23 to the power of R. Now, this is a very important equation. I'm going to call this star. I'm going to clear the decks here. Remember, X and Y are these. I don't think it's... We can rub this thing out. All right, so this is... I'm just going to rewrite this because this is an important equation here. I've got 2A plus C times 22 to the power of A. Well, let's make this in 2 to the A times 11 to the A. We'll leave this like this. 2 to the A times 11 to the A times 23 to the power of C is equal to P plus Q plus R times 2 to the power of P times 11 to the power of Q times 23 to the power of R. Now, we require a little bit of thought here. You see, this is a factorization of the same number in two different ways. Now, when you got a number, there's only one way in which you can factorize it into a product of primes. So I got 2 to the A here and I got 2 to the power of P here. So I must have that the power of 2 in this should be equal to the power of 2 on the right-hand side. But I must be careful here. Maybe there's a 2 here as well. Right. But if 2 doesn't go into this, then I will have A equals P and A equals Q And that is going to lead to x equals y. You remember x is 2 to the a times 11 to the a times 23 to the power of c and so on. And it's going to lead to x equals y, which is not what we want. So what we need to have is there must be a 2 inside here so that you get a different power of 2. And I want an 11 here as well. Then you get a different power of 11. I don't want P to be equal to A and Q to be equal to A. So let I try to explain why this is so. So you got 2A plus C. I want 2 to be a factor of that, 11 to be a factor of that. Of course, we can let it be equal to 22. That's a good choice. Right. Now, so I'm going to see now if we make this assumption, whether we can get a solution. Right? Okay, so in place of 2 to the power of 2a plus c, I'm going to put 2 times 11. So the left-hand side becomes 2 to the a plus 1, 11 to the power of a plus 1, 23 to the power of c equals. Now, it's equal to p plus q plus r times 2 to the power of p times 11 to the power of q times 23 to the power of r. Now I got this thing factorized as a product of prime numbers. And since the factorization is unique, I must have that p is equal to a plus 1 and q is a plus 1. See? Because you must have a power of 2's must be the same, the power of 11, and same with the power of 23. So let's have a look at this now. If p equals a plus 1, let's just, we have p and q now in terms of a. We've got c in terms of a also. So we're getting there. So now p is now a plus 1, right? So we can cancel. We've got 23 to the power of c. I'm taking out 2 to the a plus 1. And p is a plus 1. Q is a plus 1. Taking that out. And this is equal to p plus q plus r. But p plus q is 2a plus 2 plus r equals 23 to the power of r. Right? I'm substituting p equals a plus 1, q equals a plus 1, and we have this. Now we have an equation here. We've got 23 to some power, and we've got this is 23 to the power of r. So it follows that. Let me delete this. Remember, I'm trying to find A, B, C, P, Q, R such that f of x equals f of y. So all this is leading towards that. We can forget the goal after a certain time. We spend too much of time on this. So here, what we can do is, this has to be a power of 23. So therefore, you got the 2a. Oh, sorry. This part here, 2a plus 2 plus r must be some power of 23 because I've got 23 is a factor of this. In fact, it's the only factor. There's only one factor, prime factor for this, 23. So 23 will have to be, this has to be a power of 20. Let's call it 23 to the power of S. Right. So when you do that, then you have the 23 to the power of C is equal to 23 to the power of R plus S. So this is, we are calling this 23 to the power of S. So you have C is equal to R plus S. Now remember, we had that 2A plus C is 22. Right? So I've got these equations here now. And I can get to 2A plus C by adding. Add on both sides. So the left-hand side becomes 2A plus 2 plus C. And the right-hand side becomes 23 to the power of S plus R plus S. I'm adding on both sides. The reason why I'm adding is I know that 2A plus C is 22. So that's very nice. So the left-hand side now becomes 24 because this is 22. I'm sorry, when you're adding 2A plus 2 plus C plus, there's an R here also, plus R. This, the 4 terms here, 3 and 1. So these are 4 terms. The R's will cancel. So I got 2A plus 2. 2A plus C itself is 22. The left-hand side simplifies to this. And the R's go away. And I have this equation, 23 to the power of S plus S. Now we need to solve for S. And we can see that there's a very nice solution. Straight away, you can see by inspection, S must be equal to 1. So we can find an S, right? So now we have, I just want to put this down here. I've got P is equal to A plus 1. Q is A plus 1. And S now is equal to 1. So C, so R, we needed to find R. So you got C here is R plus 1. So R is C minus 1. Okay, so what we have here is the following. We started off by saying that suppose f of x equal to f of y, and we saw that that implies we can find x and y, but with the condition that 2a plus c must be equal to 22. So it seems that as long as 2a plus c is equal to 22, then we have a solution. Now, how can we, remember a and c are natural numbers. So there are quite a few solutions for this, but a nice solution is take a simple solution like, for example, to make calculations easy, let a be equal to 0. I can have a equal to 0 because we had 2 to the power of a. So that could be 1. So a equal to 0, but in that case, c is equal to 22. And then p is equal to a is 0, so p is equal to 1. And q is equal to 1. Right? And r is equal to c minus 1. So r is 21. So you see, or a equals 0, remember a equals b. So we said that, started off by saying we are looking for a solution when a is equal to b. So now for these 6 values, let's see whether it works. So now you'll have x is equal to 2 to the power of a, which is 2 to the power of 0, 11 to the power of b, and 23 to the power of c, which is 22. So that is equal to, x is equal to 23 to the power of 22. Right, so x is equal to that. And what is y? Y is equal to 2 to the power of p, which is 1, 11 to the power of q, which is 1, 11 to the 1, and 23 to the power of r, which is 21. Right, so we've got r equals 21. And so this is actually 22 times 23 to the power of 21. You can see x can't be equal to y because 11 goes into this, but 11 doesn't go into that. See, 11 is 22. So x is certainly not equal to y. But now, is f of x equal to f of y? So let's try. Now remember, f of 11 to the a, 2 to the power of a times 11 to the b times 23 to the power of c equals a plus b plus c times that expression. Right. So f of x, we can work it out straight away. F of x is equal to, now, it's a plus b plus c. Here you got 23 plus 0 plus 0. So it's f of x is 23 times x, right? Which is 23 it's 23 sorry, something is funny here. A equals 0, c equals 22. So f of x is equal to a plus b plus x. So, oh, I'm sorry, it's 22 here. The sum of a plus b plus c is 22. Okay, so you got f of x is 22 times x. It's 22, and x is 23 to the power of 22. So that's f of x. What is f of y? There's y here. The sum of the exponents is 0 plus, it's 1 plus 1. The p plus q plus r is 1 plus 1 plus 21. So that's 23. P plus q plus r times y. Y is this, 2 to the power of 22. 2 times 11 is 22. And it's 23 to the power of 21. Right? Now, the 23 appears twice here. So this is 22. 23 times 23 to the power of 21 is 23 to the 22. Ah, you see? Bingo. You got f of x equals f of y. And yet x is not equal to y. So that is when I take a particular choice of a and c, but they must satisfy this equation. This is not the only solution. You could put, I put a equal to 0. I could have taken a equal to 1, in which case I can get another value of a and c. It'll work for that one as well. It'll work for quite a few, but we only wanted one. Show that there exists x and y such that x not equal to y, and f of x equals f of y. Okay, it's quite a deep problem, and that brings us to the close of this very interesting and deep problem. Thank you very much for listening.